Hello, my dears. This is week 3 in module 1, the week or the material of week 3 titled as mathematical modeling. We are here in this week or in this part of the syllabus, we are going to study the modeling of electrical circuit. To understand the behavior of a system, we need to express it mathematically. We need to replace the physical system by mathematical expression. So the mathematical modeling is equation describing that system. So we are going to transfer the physical system to mathematical equation. That's going to make it easier for us to deal with it in control system. So modeling, as mentioned, is converting or transferring the physical system to mathematical equation. This week here we will start with the electrical system. We will model the electrical system. In the following week, we are going to deal with translational mechanical system, rotational mechanical system, and then electromechanical system. Here we will start in the modeling of electrical network. Electrical network consists of mainly three elements: resistance, capacitance, and inductance. That's what can be found in any electrical circuit. Just to understand something here, if the elements are not there, if these elements are not there, means the system is something else. Usually we model it or find its equivalent. We find its equivalent to put it in a form of resistance, capacitance, and inductance. Like for example, if I have a motor, the motor is not expressed as a motor, it's expressed as resistor or resistance in series with inductance. That's what he mean by that. Okay, these elements are expressed in time domain and in S domain. We are going to put them or find their equivalent in S domain direct, so that in the circuit later we are going to put it in S domain and start the modeling. What do I mean by this? The capacitor, it's going to be modeled as 1 over CS. Of course, if you look here, this is the time domain, this is the current voltage relation. So if you try to find the S domain out of it, it's going to be 1 over CS. The resistor, which as you see here expressed in whatever we have studied earlier, it's expressed in Laplace as a R. And inductor is expressed in Laplace as a LS. So now what's the importance of this? Whenever we see any of these elements in the electrical circuits, we are going to replace them by Laplace equivalent and start the modeling. So modeling, actually in modeling of the electrical circuit, there are certain equations we are supposed to depend on. The good thing here, we are going to depend on equation we are very familiar with. We are very familiar with Kirchhoff voltage law and Kirchhoff current law. Mainly we are going to depend on these two laws to model the electrical circuit. Of course, whatever theorems we have studied in electrical circuit can be used, but all of them deriving from Kirchhoff voltage law and Kirchhoff current law. So simply I can say you can use whatever theorems you have studied in circuit analysis to model the electrical system or electrical network. Kirchhoff voltage law is saying the total voltage in any loop equal to 0, and Kirchhoff current law saying the total currents entering and leaving any node equal to 0. It's very well known. These two laws are very well known to you. So we are just going to use them in model the electrical network. What are the steps we are going to follow to do the electrical network model or to model the electrical network? Whenever we get electrical network or electrical circuit, we will put it in Laplace domain. That means we are going to remove all the elements value which expressed in time domain and replace it with the equivalent as explained in the previous table, in the table of the slide given before. So we replace, so first we will draw the circuit, then we replace the components, then we will apply the theorems which we have studied. So the theorem we have studied, as I mentioned in the previous class, anything you have studied in electrical circuit analysis, anything you have studied in circuit analysis help you to model the network, we will use it here. We will see it in the example here. Like for example, if I want to find the model of this network, what's the question here? He said find transfer function VC over V, all as a function of S of the network given. So here, once he said VC over Vs, that means VC is the output and V is the input, because we know that the transfer function is the output over the input. Just keep in your mind, because you need to understand modeling here. What's the meaning of modeling? The circuit here will be finally expressed as system with input and output. The input here will be V of S and the output VC of S. So what is in this box? That's what we mean by model. What we mean by model is what is inside this box. How to develop it, that's what we are going to see in the next slide. So here we find that the relation can be found easily by applying voltage divider rule. I hope you remember voltage divider rule from electrical circuit. Notice here I'm not calculating the quantities. Last time I used to calculate the voltage on resistance, current in inductance, or whatever. This time, no, I don't want this. I want to find the relation between output and input. So this is the difference between circuit analysis and modeling. In the modeling, I need to calculate the relation between output and input. So notice here, I found that the relation between output and input, or we can say VC over S is equal to VC over V is equal to the voltage drop on the capacitor. So we will put the capacitor value 1 over CS. Remember, we are converting the capacitor to 1 over CS. Its Laplace equivalent is 1 over CS. The resistor is R and the inductance LS. So now in voltage divider rule application, we are going to put the impedance of the capacitor where the voltage drop, the voltage drop on the capacitor. So we are going to put the impedance of the capacitor on the denominator divided by the total impedance in the circuit. So it's 1 over CS plus LS plus R. Now it's a matter of simplification. After that, do the mathematical capabilities you have, or what to say, the algebra knowledge you have, to simplify the equation until you put it in its simplest form. So finally, the equation going to look like this when you simplify it. Somebody may ask why to stop here, why don't I put it in other format? Because usually in control I need the denominator to be in a form of a quadratic equation as S squared with its coefficient. We prefer always to put the coefficient as a 1, okay, followed by S with its coefficient and with plus the constant. So always we put the denominator by this way. So please care about the denominator. So now finally, instead of dealing with this electrical circuit, let me just make it clear. Instead of dealing with this electrical circuit, we are going to deal with it from control point of view by finding its model. So the circuit to me now looks like this equation with this input Vs and the output is Vc. Another example here, but in this example it seems like we are having more than one loop. So if I have more than one loop, I need to use maybe mesh analysis or any other technique given. Let us see here what he wants. Find the transfer function I2 over V. I2 over V. Remember, in the electrical circuit, the input can be voltage and the output voltage. Input can be voltage, the output current. Input can be current, the output voltage. Input can be current and the output is current. I mean, any of this can be. So here he asked me, he tell me what is the input, what is the output. Usually the question will indicate which one is the input, which one is the output. So he's saying here the input is V, notice it's V of t, and the output is the current in this loop, which I2. So the first thing, according to the steps mentioned earlier, I will redraw the circuit. You will see it in the next slide. Then I will replace the quantities here by their Laplace equivalent. Let's see in the next slide. So we redraw the circuit and we put the quantities in Laplace, as you see here, all the quantities expressed in Laplace. And then we will find certain technique to answer the question. Of course, we have to keep in our mind that we are looking for a way to relate the output to the input, I2 to I1. So the easy way here, or the easiest way, is applying mesh analysis, which we have studied earlier. So let us apply mesh analysis. To apply mesh analysis, we have two loops here, as you see, loop of I1 and loop of I2. So this is equation number 1 for loop 1. How to develop the equation in easy way? Easily we can say we are going to find the total impedances in loop 1, total impedances in loop 1 multiplied into I1. Total impedances in loop 1 multiplied into I1. This is positive. Notice this is positive. Now minus whatever impedances between I1 and I2, means the impedance which linking the two loops, which having two currents in it. Because in this impedance we have I1 in and I down and I2 up. So two currents are in. So this kind of impedance we put it as a minus LS into I2, the other I, equal to the total voltages in loop 1. Total voltages in loop 1 means only Vs. That's how we can develop the first equation. So the first equation is developed. Similarly, we can get the second equation, where in the second equation we are going to follow the same sequence. Here I start with I1 followed by I2, then the constant. Here I will start with I1, then I2, and so on. So I1, when I am in loop 2, I1 is the other current, So I will consider it minus sign, minus, and it's going to be I1 multiplied into the inductance or the impedance in between the two loops, which LS. That's what's shown here. L minus LS into I1 plus, since I am in loop 2, I'm calculating for I2, the sign will be plus. So plus the total impedances in loop 2 multiplied into I2. Notice the impedances in loop 2 here. Impedances in loop 2 are LS plus R2 plus 1 over CS, all of them multiplied into I2, equal to the total voltages in this loop equal to 0, because we don't have any voltage source in this loop. There is no voltage source. That's why we put it equal to 0. So here we develop equation number 1 and equation number 2. We solve the two equations. Solve them. I think the easiest way to solve them is using a Cramer's rule, as you see here. So by Cramer's rule, what I need to calculate? We need to calculate I2, of course, only I2. All what I need is calculating I2, because by calculating I2, I will find it's calculated in terms of V. So we will rearrange the equation to get the required quantities. Okay, what is delta here? He put delta. Delta is the coefficient of I1 in equation number 1. Let me just erase this. Delta, if you forget this one, this is delta. It's this element with this element and this element with this element. This is delta. Okay, so when we put this determinant in the denominator, solve them, we are going to find the solution in the next slide. Notice here this is delta, as I mentioned, and we substitute it in the previous equation. We are going to find the GS, which equal to, by rearranging, I mean it as IS over V, we are going to get I2 over V equal to this quantity. which means what the equation mentioned earlier, if I look at it as IS over V, means the output is IS, the input is V, its transfer function will be this one. This is the transfer function. So again, to remind you, it's mathematical expression describing that kind of circuit, with the input is Vs and the output is I2. How about if I want to calculate it for V2, for example, or V on the capacitor? Or of course, it's going to be different transfer function. So whatever change happened to the output element or the input element, of course, it will be different transfer function. Like if I want to calculate it as the input is Vs, the output is the voltage drop on the capacitor on the other side, the transfer function will be something else.